Hello my dear Pymarads and welcome to a new chemistry project, in which we are going to look at all the water molecules in the world's oceans, learn what is Avogadro's constant, talk about isotopes. All that with help of Python of course, its statistical module scipy.stats, some for loops, binomial and other statistical distributions, and some feared unit conversions. I'm very excited about it and I hope you will get stunned by the numbers which come out of this one. One question for you. Have you ever peed in the sea? Even if not, I promise thousands of people are doing it right now. And based on this maybe enjoyable but also abominable activity, we are going to create our chemistry experiment. So, you pee in the 300 milliliter glass and pour all of it in the ocean. Then you wait until all the ocean perfectly mixes, which takes too long, so we only assume that everything will get perfectly mixed. And then you draw the same glass of perfectly mixed sea water back into your glass. The questions are the following. What is the average number of molecules of your pee in that glass of water? And what is the probability of having more than 2300 molecules of your pee in the glass? And finally, if we take one of the strongest poisons in the world, polonium, how many atoms in your glass would actually kill you? You can try to solve all this in a guided way by opening exactly this interactive notebook on the server via the link in the description of the video. There is also a solution notebook where you can discuss and compare your solutions. I will walk you now through the main ideas. First is that we are going to import some modules. Some of the modules you already know, for example numerical Python, NumPy, S and P, and also matplotlib pyplot as PLT. Above that, we are also going to import statistical modules scipy.stats and scipy.constants, which contain all the possible physical and math constant values together with their units as well. Then the real task starts. We need to first find how much water is there in the world's ocean in total. And that is what Wikipedia pages are for. And we will find that there are lots and lots of cubic kilometers of water. But we need to convert it to liters, so that's what we are going to do. And after that we need to figure out how many actual molecules are there in 1 liter. For that we are going to need to learn about the unit mole, Avogadro's constant, and how it relates to the weight of a water molecule. Once we have a weight of a molecule, and you surely know the density of water, we will be able to calculate number of molecules in 1 liter of water. I will also make some vaguely connected side notes on isotopes, in particular isotope of carbon, because that's how Avogadro's constant is defined. Based on the above, we can figure out how many total water molecules there are in all the oceans in the world. And then we do the same logic for molecules in the glass of pee. Taking the ratio of these two numbers, amount of molecules of pee over the total number of molecules in the oceans, we arrive that no matter how much you dilute your pee in the sea, you will still have around 2200 pee molecules in the glass. This result still amazes me, but it is really true. The second question is much harder, because probability of drawing more than 2300 molecules means that we basically need to know probabilities for possible results of drawing 2301, 2302, etc. And only then we will add them all together to arrive at the total probability of drawing more than 2300 p molecules to your glass. If you imagine a bag of molecules and drawing molecules has only two results, either success, p molecule, or failure, drawing an ocean molecule, this is a standard example of so-called binomial experiment. However, if we are not replacing molecules in the ocean after each draw, strictly speaking, we need to use so-called hypergeometric distribution. And I will show you how they compare to each other in a short example. So in the end, you will be able to plot the distribution, in this case binomial, for 5 draws out of a bag of molecules, and then we will create the same distribution for hypergeometric case and how they compare and how the probabilities are different. And you see here that on the y-axis we really have the probabilities. Very useful thing to calculate, and in Python it's extremely easy. In fact, it takes only one line of code. Interestingly enough, if we are going to increase the total amount of molecules in our bag, the hypergeometric distribution will be progressively more and more similar to the binomial one, until they are completely unrecognizable. And I will show you a method how to monitor this difference and decide how big of a bag is big enough in order to use binomial distribution. And that's where the for loop comes in. So we want to monitor difference between distribution. So we create an empty list, and there is a lot of text to explain you what is happening, but for each size of the bag between 20 and 2000 molecules, we are calculating the difference between the binomial and hypergeometrical distributions. And then we take the absolute value in order not to cancel out the positive and negative differences, and we make a sum of all those small values and add it to our difference list. And we run through this so-called loop, basically 2000 times almost, and the result is almost 2000 numbers added to our difference. And then we can plot this difference depending on the amount of molecules in the bag, and we see that the difference between the two distributions will be decreasing. And in this method, you can decide what difference is good enough for you to use one distribution or the other. And this will work very generally for many kind of problems when you are not sure how to proceed. In the end, we really can use the binomial distribution and we can now generate it. Since we know that in average we draw 2250 molecules of our own P to the glass, we create an array values for possible results around this value, and then we generate the distribution by our binomial PMF method. And here we see the possible results between 2000 and 2500, and for each result we have on our y-axis the true probability of drawing that many molecules into our glass. This means that there is basically a zero chance to draw only 2000 molecules of your own P into a glass. There will be always more. To really nail down the number of getting more than 2300, we are going to sum all these probabilities for the results 2300 and more. And this is done that we need to find out the index for 2301 and then sum all the probabilities which come after. We can also use so-called cumulative distribution function. I will show you that, which looks like this, and it's all explained in the notebook. As a bonus, since we have the whole distribution, we can retrieve also so-called standard deviation, which kind of tells us what is our statistical randomness of our results. By definition of standard deviation, there is a 68% of chance of drawing somewhere between our mean value, 2253, minus standard deviation, until our most probable result plus standard deviation. In the final part of the project, we take one of the strongest poisons in the world, polonium-210, which takes only 1 milligram to kill a human being, as shown, for example, for poisoning of Alexander Litvinenko by Russian KGB in 2006. The question is, how many atoms does it correspond to, this 1 milligram, and how does this number compare to our 2200 P molecules in our glass? So we need to find out again the mass of polonium, and then we can calculate the lethal dose in amount of atoms. This is again a huge number, which makes the same point as we already mentioned, and it is also our conclusion. 2000 molecule of P in your glass may feel disgusting, but it is truly a minuscule number, and you cannot get poisoned by any of that. In other words, Avogadro's constant is huge number. And there are some other conclusions and some other particular questions which you can explore more. I hope I got you excited to try this project on your own, in your own pace by opening the interactive notebook in the description of the video. There is also a link to the solution notebook, which you can also run all the cells, plot the graphs, think about what is written in the text, or find another project which is more appealing to you. And please come back to me with some comments, questions, suggestions, what would be interesting to calculate more based on this project. See you soon at the other one. Bye!